Hi, I'm going to make a series on assembly language and reverse engineering. There are many ARM families and ARM architectures. ARM families are like processors like AMD64, which is used in Windows, and Snapdragon, which is used in the Android mobiles. Each ARM family supports one or multiple ARM architectures like x86 64 architecture by AMD64 and ARMv8 by Cortex A53. You can see ARM Cortex A53, which is MediaTek processor. You can find all the ARM families and architectures on Wikipedia website. Each ARM architecture has different instruction and register. For example, in x86, which is a 32-bit system, we have 6 general purpose registers, while in ARMv8 we have 30 general purpose registers. ARMv8 is mostly used in Android phones. In this course, I will cover two main architectures of assembly: ARMv8, ARMv6, and ARMv7. We are not covering ARMv8 right now. We are covering ARMv6 and ARMv7 architectures. First, let's learn how the compiler, like C++ compiler, compiles the file. It takes the source code, pre-process it. Pre-process means removing the includes. On top, you, for example, you include IO streams. It will remove it and add their code in place of includes to create a single file, and forward that single file code to the compiler, which generate the assembly code. These assembly codes go to the assembler. Assembler creates bytes file called an object file. This object file then gets linked or loaded to create an executable file like exe. I am going to code directly in the assembly. Use the assembler to make an object file and use the linker to make an executable to help you understand the assembly language better. But first, learn how to write assembly language. Before writing the assembly language, there are concept of registers. You need to understand in assembly language you can only store data in these registers. Similar creating to the variable in C++. In ARMv6 there are 30 general purpose registers, but we can only access the first 16 registers. These 16 registers are then divided into two main groups: general purpose registers and special purpose registers. From R0 to R11 there are general purpose registers, which are like variables where you can store numbers. Special purpose register serves different functions. Now you may be wondering about R12, R13, or 14. I will discuss them later when we talk about the stack. For now, R15 register, which is also known as program counter, it contains the address of the next instruction which program is going to execute, and CPSR, current program status register, contains the flags. From flag I mean that if your number goes to negative, then negative flag will be set. Like negative 13 is a number, then negative flag will be set. If you multiply numbers and get a carry, the carry flag will be set. For now, if we only need these two flags. We will discuss other flags when exploring buffer overflow vulnerabilities. We have discussed quite a bit about ARM registers, and I know it might be getting bored. So let's visualize these registers. But first, set up the lab by going to Azure Lab website, Azure Labs. Click on the Azure Labs tutorials. Then from Lab Environment drop-down, click ARM Lab VM 1.0. It is pre-configured lab for ARMv6 architecture. Scroll down to the download links. Download the lab from the Google Drive. The password for the zip file and Ubuntu is Azure Labs without spaces. You also need to download VMware Workstation to use this lab. Search for VMware download. Download it for your system, Windows or Linux. Install it. Then unzip your Azure Labs file you downloaded from the Google Drive. Double click on the Azure Labs V1 VMX. It is the file inside the Azure Labs uh, lab you have downloaded from the Google Drive. It will open in the VMware. Then click on power on this virtual machine button to start the machine. If it shows a pop-up asking if you have copied or moved this lab, just click I copied this lab. Once your lab is open, you will see emulate Raspberry icon on your left panel. Click on that. It will take some time to initialize our environment. After it initializes, change the workspace by clicking on the top right corner of the screen and to workspace 2. But first, let it finish to initialize our environment. Now click on workspace 2. Here you can see SSH into Raspberry. Click on that. Make it a little bit bigger and zoom in. You will see some folders. By typing ls, the ASM folder contains some sample assembly code. Don't worry about them for now. In the future, we will make complete programs from scratch. One more thing, let's check our operating system architecture by typing uname -m. As you can see, we are using ARMv6 architecture and we can compile ARMv6 assembly code on the system. I have made a sample program. I am attaching that program to the GDB debugger to see the registers in action. To activate GDB, just type GDB and the executable name. In my case, it is MOV and hit enter. I know that in my code I created a function called start, so I am going to set a breakpoint on that function. Breakpoints means that program stops when it reaches that point. We will discuss all details later. For now, set breakpoint by using br and the function name start. Now we have set the breakpoint. We are going to execute the program. To run the program in GDB, use the run command and hit enter. As you can see, all the registers here from R0, R1 to R9, and so on. Others initializes all up to R12 by 0, means these contains nothing right now. And CPSR register is not set. When it gets set, the highlighted and bold flag is set. For now, I am ending this video. If you like this video, we can continue this series. To learn more, leave your comments and tell me if my teaching method is wrong or I made some mistakes. I will try to address that in the next videos.